have this picture wildlife preserves. So we'll start with an introduction and we'll present the model, the hierarchical structure. We'll move to influence and we'll consider three types of influence. Two types for approximated methods. First order conditional expectation. Maximum likelihood, probability model, and Bayesian approach. Next, we'll briefly review differential model, ordinary differential equation, stochastic differential equation. Then, we start the example using three different software and then mixed, as we already used it yesterday, but two new ones, Monolith, which needs MATLAB, and Winbug, which needs Windows. So I imagine everybody has downloaded MATLAB, as we told you. Everybody has a MATLAB? Okay. So, the classical way to write the nonlinear mixed model is as follows. Write that the response for individual I and measurement J is equal to the function of some variable Tij. Tij can be, for instance, time. In our example, growth curve, it could be time, it could be dose, concentration, something linked to the process. And Ti are parameters varying across individuals, plus a residue, Eij. Now, we present this model according to a hierarchical structure. It's really useful for influence. So the first step is to define the conditional distribution of a response given this individual parameter, I. And we consider the expectation and the variance of this conditional distribution. So the expectation is f of Tij Pi. In fact, we represent this under vector notation. So if we consider for this individual all his measurement, 1 to ni, we can represent this function f as this bold fi, function of Ti, the corresponding vector of time of measurements for individual I, Pi, and this vector is made on the different f for each measurement, Ti1, Tij, Ti, and I. So we write the conditional expectation of this vector having this form. First, couple of examples we'll use. Linear, if it works for nonlinear, it should work for linear. Remember what we have seen in the first lecture about longitudinal data, the cutoff and right data. We can write that the conditional expectation of the Yij equals phi I1 plus phi I2 Aj. Phi I1 is the so-called intercept, and phi2 is the slope. Tij is the age. We'll see today another example, a real nonlinear example, describing growth curves via the Gamper's function. Gamper's function has this form, one of these forms. It involves three parameters, phi1, phi2, phi3, according to this expression, phi1 exponential minus phi2 exponential minus phi3 tij. Another function I reported to describe logistic growth curve, and that might be useful for your project. Remember, you have projects. You will work on projects tomorrow, or you will work for projects. Has been proposed by Davidenko in his book in 2004. Is a quartic logistic growth function which involves four parameters: phi1, phi2, phi3, phi4. No, go ahead. Allez-y. Merci. La salle va sourire, donc ça sera pas bien. Non, allez-y, non, il n'y a pas de... Non, je ne sais pas, demander peut-être s'il y a des stars. C'est cher. According to this expression, phi1 divided by 1 exponential phi2 minus phi3, tij minus phi4, tij squared. This is the kind of function you can use on your project on height of children. Next, we consider now the variance of the conditional distribution of the response given the parameter, and in fact this will be the variance of the residual. Ei equal yi minus fi. And this residual is the same as we have seen for linear models, can be decomposed into two components, EMI, a pure measurement error, and ERI, representing the deviation of a real process from the process described by F. And this ERI is similar to what is called a nugget effect, for instance, in spatial statistics, and it's linked to this phenomena of autocorrelation. Most time, nevertheless, most time there is no precise distinction between the two. And usually we will put together these two components and we'll write that the conditional variance is the residual variance, and we'll use Ri to denote this residual variance. Potentially this Ri is a complex function. It could depend, it may depend on the individual parameter, and it may depend on specific parameters. And we will see that tomorrow, how to model this residual variance, especially nonlinear mixed model. But today, we will stay with this very simple assumption, sigma square, homogeneous, and independent residue, non-correlative residue. And usually we make the assumption of normality on the residue, ER norm of 0 R. But we'll see that tomorrow. So that was the first stage of the yard. Now the second stage, first stage was distribution of yi given the parameter phi I. Now we will look at the distribution of phi I. How to model phi I. So to account for inter-individual variation, we set up a mixed model on this phi I. That means that for one component, remember, we may have several components, two in the linear case, three in the unpaired. So for one component, we will write phi IL equal A prime IL, incidence, rho, beta L plus UIL. So if we collect all the components, we can write that under the vector form, phi I having the M component equal AI and B, incident matrix, M rows column, beta, fixed effects, plus UI, centered random effect, M components. We can alternatively write this as phi I distributed. We'll see what kind of distribution with expectation AI beta and variance covariance matrix G0. Usually, we'll assume normality on the phi I or on the log of some components. For instance, in some field, in pharmacokinetics, pharmacodynamics, they usually assume log normal. That means normal on the log. So we will see in using the software that we can choose between the two at start, or test. And if the log, if the normality of log is more appropriate than the normality of function. So PI is an incidence matrix, P corresponding to P covariates with coefficient P. UI are the random effects using the traditional parametrization G0, G0. So again, I come back to my example, and the last one, the logistic. So, in fact, we are doing the project already, so it will mean less work for you. Phi1, Phi2, Phi3, Phi4. Remember, in this project, we are describing height of boys and girls. So, this Phi will depend on the gender or the sex of the child. So, for instance, we could write Phi1, if we take as reference the girls, is equal to mu1j for girl, plus an indicator variable indicated if this individual is a boy or not, times a beta, and if, having taken this as a reference, the beta will measure the difference between boy and girls. The coefficient of the indicator will measure the difference between boy and girl, plus the individual deviation I1. So we can write I1 equal 1, the indicator u1j, beta 1, boy minus girl, plus I1. So we write A prime I1, beta 1 will be this, plus I1. We'll make the same decomposition on the other components. Phi2, u2j plus the indicator variable beta 2, boy minus girl should be a b, boy minus girl, plus ui2. So we'll write again a I prime should be a 2 here, not a 1. Correct it from your handout. Beta 2 plus ui2. And same for phi I2, I3, phi I4. Notice that in this case, all these incident throws are the same. They are represented by 1 and the indicator being above. So we have A prime I1, A prime I2, A prime I3, A prime I4 equal A prime I. Now, regarding the structure of UI, 4 elements mean 0 and structure variance covariance with different variance and different covariance. Next. So that's all for the model. Now we'll enter in the tricky inference, and in fact we'll suffer more for describing the approximation than for describing the exact methods. So we'll start with the first order linearization. And oddly enough, you will see close relationship between what I told you and what Florence told yesterday. But as GLM and NLM are separated words, they use different names, again, to say the same thing. So you will realize yourself the connection between the approximated procedure in GLLM and NLLM. So the notation, as before, UI, we'll put all the parameters in this theta vector. So we have the fixed effect, we have the components of the variance covariance, G0, and we have the residual variance. So what we are going to do, we are going to make a Taylor expansion of this function around UI equals 0. This should remind you something we have seen already yesterday. So we'll write fi ti phi equal this function for UI equals 0. That means fi ti a I beta, because for UI equals 0, pi equals this, plus the derivative of phi with respect to ui, evaluated at ui equals 0, times ui. So now what is this vector, of this matrix of derivatives? We should have as many rows as fi, and fi, remember, is the vector of the measurements for individual I. So it should have ni rows, and it should have as many columns as ui, and we have n components in ui. So that's n components. And it's built that way. So we'll take here the f for measurement 1 everywhere, and we'll have derivative with respect to ui1, ui2, uin. So forth for the jth measurement, the same everywhere, and ui1, ui2, uin. So this row is z prime i1 tilde. We call it z prime i1 tilde. This row is z prime ij, and so forth. And we'll build this matrix we'll call z prime z tilde, sorry, i. Ni rows, n columns. And it's a function of ai and beta. Since ui, it's evaluated at ui equals 0.